afterwards, we just have 10 minutes for a quick switch between all the different sessions. I'm proud to present Mario Fusco, and here we have someone from Italy telling us what's the hot thing in Loom.
Okay. Thanks, Ayol. Thank you for coming. I'm from Italy, indeed. I work for Red Hat. I am the project lead of Rules, which is our rule engine. And in the last time, I played a bit with Project Loom, with Virtual Thread. And the purpose of this talk is just bringing my experience on this new technology. Okay, so let's start with a very quick introduction about what Virtual Thread actually are. We all know about native thread. We use native thread of the JDK. At the moment, are still the only thread technology available on the JDK. And they actually are just a thin wrapper around the threads that are borrowed by the operating system to the virtual machine. So the Java virtual machine just uses the operating system thread, do something around them, it's really a thin wrapper, and use them as they are. This means that in general, the operating system thread are a costly resource, a memory-consuming resource, and for this reason, they are a scarce resource in your virtual machine. And that's why you cannot have too many of them. Okay, this is the main problem. With virtual thread, we try to remove this problem by getting rid of the one-to-one relationship between the operating system thread and the Java virtual machine thread, meaning that in this way we can multiplex multiple virtual threads on the same native threads. In this case, the native thread is called the carrier of the virtual thread, and we have many virtual threads running on the same carrier, of course, using the same carrier at different time, of course. And this is one feature of virtual thread. The other important feature, probably the most important one, is that they do not block, meaning that when you do a blocking operation on a native thread, you are blocking the thread. That thread cannot be used anymore in that period of time. And as I said, this is a scarce resource. You don't want to be in this situation. With virtual thread, it happens exactly the same. You are blocking the virtual thread, but this time you are blocking only the virtual thread, not this carrier. So when the virtual thread does a blocking call, it is detached, temporarily removed from the carrier, meaning that the carrier can be used by another virtual thread to do its own job. And then you are no longer blocking a scarce resource instead. And in this way, you can have many virtual threads doing their stuff on this carrier thread. I'm speaking about this carrier thread. The carrier thread in the current implementation is provided by a pool. It's a specific pool of the Java virtual machine, which is a fork join pool implementation at the moment. Okay, so what I'm saying is that the main differences between the native threads and virtual threads, and the reason why you can have many virtual threads, is that typically a native thread has 2 kilobytes of metadata, while virtual thread has around 200 or 300 bytes of metadata. Yeah, and this is one small difference on the memory consumption, but the biggest difference for what regard the memory consumption is how the stack is allocated. When you create a native thread, you have to pre-allocate the whole space in memory that is necessary for a stack. Regardless if you have a stack that is deep 2 methods or 2,000 methods, you have to pre-allocate 1 megs of memory for that native thread to be used, and it's reserved to that thread, okay? With virtual thread, you have a pay-as-you-go stack, meaning that it's a data structure. It's actually a stack, but it's not in a reserved area. It's actually on the heap on the virtual machine. So this means that this data structure, the stack of a virtual thread, can enlarge and shrink based on the needs, based on how deep is your stack or is the stack of the virtual thread in that moment. And the other important difference is that for context switch, and this will be important for performances, as you will see later. Context switch for native thread is performed in the kernel space. It's quite expensive. While a context switch for virtual thread, they are data structures in the virtual machine. So it's not performed by the in kernel space, it's performed in user space. And this means that it's generally 10 times faster, okay? So with all these premises, the selling point of virtual thread, the way they started saying, okay, virtual thread are a cool thing, is saying, finally we can have millions of threads, okay? And when I heard this claim from, for the very first time, I was a bit surprised, let's say, okay? Even because I remember that a few years ago I gave a presentation about the different kind of concurrency model that are available on Java, on the Java virtual machine. And I remember that when I was speaking about multi-threading programming, what happens generally, or at least this is what happens to me, is that you designed your multi-threaded application in this way. Of course, what happens in reality is this. And so I was a bit surprised because my question was, okay, do we really want a million of puppies doing this in our virtual machine? I mean, I know puppies are nice and cute, but probably we don't want to get there, okay? So the main selling point, in my opinion, is not that you can have millions of threads. Okay, this is true, you can have millions of virtual threads, but this is just a side effect of how they are designed and how they behave. Okay, it's not, in my opinion, again, the main selling point of virtual threads. So what are virtual threads really good at? For which reason should we use them? How many of you does some sort of reactive programming? Okay, a few. And I believe that you know, are you happy with it? I mean, it's easy. The problem is that doing reactive programming in reality is pretty hard. Why are we doing this? Once again, because native threads are a scarce resource. We want to use them in a better way. We don't want to block a native thread or the event loop doing a blocking call, but we want to reuse that scarce resource to do something else, and that's why we introduced reactive threads, okay? With virtual threads, we have exactly the same feature. It is exactly the same feature provided by reactive programming, but without paying the cost of the complexity of the nested lambdas and callbacks, or the truncated stack from which we cannot understand where the problem is, and so on. Okay, so what I'm saying is that if there is one thing that virtual threads are good to do, is just waiting. Because when they wait, they are not consuming resources in a wasteful way. If you make a native thread to wait, you are using that native thread and nobody else can use it. If you make a virtual thread to wait, the virtual thread can be removed from the carrier, from its native thread, and the native thread can be reused for something else, which is exactly the same thing that you do with reactive programming, but without, again, the craziness and the verbose and the complexity of reactive programming. Okay, so when I first see this thing for the first time, another analogy come to my mind and say, okay, this makes sense. So we can say that Loom is for reactive programming what lambdas have to be for functional programming. What I want to say, okay, we all know Lambda, they are nice, we can write this thing with a couple of Lambda expression, filtering the name of all the person with a name that starts with the letter A and then some their age. It's all nice, but do we need Lambda to do this? Actually, no. If you think about it under a syntactic point of view at least, Lambda are just syntactic sugar for anonymous inner class. You can do exactly the same thing with anonymous inner class in a much more verbose way. Of course, you don't want to do this, okay? And in the same way, I think that Loom is syntactic sugar for reactive programming, okay? Of course, I put this opinion in a tweet because why not? I got a very nice reply from Ron Plessler, who is one of the project lead of Project Loom, and that's why I love Twitter. And he says, okay, you are right, but you are telling only half of the story. The other half of the story, the biggest part of the work that we did is about observability, because we had to create this abstraction of virtual thread, but we have to do it in a way that they are totally similar, indistinguishable on a machinery point of view from native thread, meaning that if you have an exception in a virtual thread, you have a proper struct trace as you have with native thread. You can observe, have a thread dump of all virtual thread exactly as you have with native thread. So there has been a lot of work that has been done to preserve the observability of virtual thread in the same way you are used to have with native thread, okay? So yeah, this was a pretty, it is a pretty long thread actually on Twitter if you look for it. And yeah, it could have been a blog post, it was just a conversation on Twitter, sorry about this, but this happened quite frequently to me, I don't know why. Okay. So what I wanted to say also is that, okay, we are speaking about virtual threads. They are good, they are nice, but they are not a drop-in replacement for native threads, okay? We are not removing a native thread from the virtual machine and only using virtual thread. They are just a new tool that we have. So from now on, we have these two kinds of thread, and we have to know the characteristic of both virtual and native thread to decide which is the one that best fit our problem at end, okay? And in order to do so, we also need to be aware of some possible also performance issue or different behavior that you could have with virtual thread. One of the first again, possible problem is that, as I said, you don't have a reserved area for the stack of virtual thread anymore. It's just a graph of object, a data structure, a data structure in your heap, okay? So it's like any other object in your heap, it has to be managed by the garbage collector, meaning that when the stack of virtual thread increases or shrinks, the garbage collector has to take care of removing the old stack, the old stuff, and when a virtual thread finishes, when a virtual thread dies, the garbage collector is also called to collect all the data structure used by that virtual thread, okay? So this means that at least in theory, virtual thread causes a little more pressure, a little more work on the garbage collector, okay? Once again, I had this conversation with Ron Plessler. Once again, he told me, yes, this is true, but also half of the story. The other half is that if you think about it, what happens is that with native thread, each and every native thread is a GC root, okay? So if you have 1,000 of native thread, you have 1,000 GC root, you have 1,003 that have to be analyzed by the garbage collector. Virtual thread instead are just a data structure, as I said. they are not GC root. So if you have 1 million virtual thread running on 8 carrier, you don't have 1 million GC root, but you just have 8 GC root. And in this sense, the work of the garbage collector is a little easier. Okay, so pros and cons. The other very important thing to know is and to avoid is spinning. What is spinning? In some I said that when a virtual thread performs a blocking operation, it is removed from its carrier. The carrier is freed and can be mounted on another virtual thread and let the other virtual thread to do its job. Okay, this is almost always true unless the virtual thread is not pinned. Pinned meaning that the virtual thread is locked with this carrier, so when the virtual thread blocks, in that situation, also the carrier blocks, which is the thing that you don't want. Especially this happens in a synchronized block. When your virtual thread is in a synchronized block, it is pinned to its carrier, so if you perform a blocking operation inside a synchronized block, then you don't have that effect anymore that only the virtual thread is blocked. In that case, you are blocking also the carrier, and for sure this is not something that you want. Another possible issue is cache misses. Okay, one thing that I didn't say is that when a virtual thread is blocked and it's interrupted, it is removed from its carrier, and then when the blocking operation terminates, it is waking up and restart its work. But when it restarts to work, it's not said at all that it will restart on the same carrier. It can be assigned to a different carrier, so continue its work on a different native threads, okay? And this especially happens with the current scheduler that we have, because the fork join pool is based on a working stealing algorithm, and this make much more likely that a virtual thread will be waking up on a carrier that is different from the one where he went to sleep, okay? And when this is happened, this means that maybe you will have quite a lot cache misses, because you are running on a native thread here, and all the cache locality is on the core where that native thread is running, and then you stop working there, and then you are resumed on a different native thread that runs on a different core, and then you will have a tons of L1 and L2 cache misses, and you will have to recreate the state on the different core. So what I'm saying is that this machinery, and especially again the work stealing algorithm used by the fork join pool, can be a source of cache misses. Another issue is that virtual threads are not preemptive. Okay, what I mean with this is that I said that when a virtual thread performs an IO operation, when a virtual thread blocks, that virtual thread is removed from the carrier, and that carrier is available for to do something else for a different virtual thread. Problem is, what happens if the virtual threads never blocks? What happens if the virtual thread performs a purely CPU bound operation and never blocks? Yes, in that case, you don't have preemptive, meaning that the virtual thread will perform its operation till the end, and in this case, in multi-threaded application, you basically lose fairness, okay? I have a very simple example to demonstrate this thing. Here I have a very stupid CPU-bound task. I'm counting 10 millions number, just counting them, and I'm doing this work within a big integer just to make it even more expensive for the CPU. So it's a really CPU-bound task, not doing anything useful, but keeping the CPU busy. Okay? And then I wanted to put this method at work with both native and virtual thread to check the differences. So I I created this method that runs this CPU-bound method 8 times multiplied by the number of core on my machine, which are 8 as well. So I'm executing, basically I'm executing this thing on my machine 64 times in parallel in 64 different threads. And these threads can be either native or virtual, okay? So I have this Boolean switch. So when I'm using virtual thread, I'm performing this runnable operation, this CPU-bound task inside the virtual thread. Otherwise, I'm creating a cached thread pool, and I'm running that operation in a native thread. And I'm also flagging this thing as a daemon for native thread. And by the way, this is not necessary for virtual thread because they are all daemon by default. You know what daemon means, right? It means that a daemon thread alone is not enough to keep the virtual machine alive. So the virtual machine is alive until there is at least one non-daemon thread still running. So I can run this thing with the native thread first. And if you see, it will take a few seconds. And I'm printing some statistic here. And if you see the duration of the 64 different tasks, you can see that it's more or less equally distributed around 2.5 or 3 seconds. And actually, the average is 2.8 seconds in this case. Okay, maybe remember this number. So let's try to do the same exercise with virtual thread. And you will see what I mean when I say that they are not preemptive. You see a totally different behavior now. So you can see that the first 8 threads are taking the CPU until they are not done. And then only at that time, you see the gap between the 8th and the 9th thread. Only at that time, the other 8 threads are able to take the 8th carrier of my fork join pool. And you see another block of 8 thread. And then you see another gap here, and so on and so forth, okay? So this means that the min and max duration is a lot different here. And the other thing to notice, which is interesting in my opinion, is that, okay, the average duration before it was 2.8 seconds, if you remember. Now it is just less than 2 seconds. Why? Are virtual thread magic or are faster? No, it's just because fairness has a cost, of course, okay? So with native thread, you have preemption that gives you fairness, but to have this, you have to do much more context switch, which are in the kernel space, by the way, for native thread. So in this way, with native thread, you have fairness, but of course also fairness have a computational cost, okay? Question about this? Okay. Okay, so to recap, yes, you can run, of course, CPU-bound task inside your virtual thread, but be aware that you don't have preemption, and this means that you don't have fairness. One last issue is that virtual thread works with threads local, as you expect, but the problem is, since you normally have thousands of virtual thread, you will have thousands of instances for the same variable in your thread local, and it will increase a lot the memory occupation. So I don't know, fortunately now we are not, there is not need to do this anymore, but for instance, I remember that since the date formatter was not trade safe data structure, and it's something we want to reuse quite fastly. What we did in the past, to be smart, is putting the data formatter in a thread local. So each and every thread could use the data formatter in a single threaded situation. Of course, if you do this with virtual thread, you will end up with millions of data formatter in your thread local space, and it will just increase a lot the memory occupation. So what I'm saying is, okay, personal opinion, thread locals are generally a code smell. I don't like them. But for what regards their usage with virtual threads, they works. But if you use them, you will have a far bigger memory occupation. So I suggest you not to do this. Okay, so these are the possible issue with virtual threads. So I wanted to give you an introduction to virtual thread and to explain how they works and the pros and cons. And then, of course, I wanted to put this in practice. So I wanted to play a bit with them and do some benchmarking and profiling to just to figure out if they maintain their promises, if they work as I expected and as I hoped. To do this, I played a bit with different test cases, and then I found this very nice project made by an American friend. I found this on GitHub, and I decided to fork it and to use it for my benchmark. So what this thing is, this is a game of life implementation. I hope that all you know the Conway's game of life, right? There is this board with the cell that can be alive or not with a very, very simple algorithm. I will be back on this later. Elliot implemented this particular instance of the game of life with a technique, a concurrent technique that is called communicating sequential processes. In all honesty, I didn't know much about this thing before giving a look to Elliot example, so I had to look about it on Wikipedia, and it's a quite complex thing with its own algebra. There is a lot of theory behind this, but in practice, what CSP is that it is a concurrency model where the only synchronization primitive among threads that you have is communication. Okay, so you basically communicate between thread using a channel. So one thread write on a channel, okay, this is my result, now you are ready to run, and then the other thread take that result from the channel and knows that, okay, now it's turn to do something. Okay, so the only synchronization primitive is communication. So this means that you need to provide a mean for thread to communicate. The simplest one, the one implemented by Elliot, was with this blocking queue. So a thread writes something on this blocking queue, and there is another thread reading from the blocking queue, waiting for a value to be present on the blocking queue, reading it, and then doing something. Okay, so this is how a cell in this game of life is made. There are a cell, of course, needs to communicate with all its neighbor to know their state and calculate its next state based on the state of the neighbor. So you have a two set of monodirectional channel. One set is used by the cell to communicate to the neighbor its own state, and the other set is used is in the other direction. Is used to read the state of the neighbor. Okay, and then you have two more channels that are that links this shell with the coordinator. One is used by coordinator to give a tick signal to say, okay, now I'm ready to calculate the next frame. And the other is in the opposite direction to give a chance to the cell to tell to the coordinator if the cell itself is alive or not. Okay, that's all. So you have this list of channels, and each and every, the idea is to run each and every cell in its own virtual thread. Okay, so if you have a board with 50,000 cells, you have 50,000 plus one virtual thread. The plus one is the coordinator. And you have literally thousands of threads doing lots of blocking operation, because every time they read or write in this channel, they perform a blocking operation, which is exactly one of the ideal working condition for this virtual thread technology. Okay, so I said that the cell does its own duty cycle inside the virtual thread. What they does is pretty simple. They they wait for the tick signal from the coordinator. Then they write their state on the attribute channel, so they notify all the neighbor of its own state. They read the state from all the neighbor. They sum the number of the neighbor that are alive and decide if in the next state they will be alive or not, using the well-known game of life algorithm. Okay, so a cell is alive if in the former step at least 2 or 3 neighbors are alive, and it was alive before, or there are exactly 3 neighbors alive. This is the game of life algorithm. Okay, and sorry, and what the coordinator does, it's even simpler. It sends a tick message to each and every cell. Is itself, as you can see, the coordinator is itself a virtual thread. So what it does is starting each and every cell and then starting itself inside another virtual thread. Then it sends in its own loop a tick message to all cells, and then wait for the cell to say, okay, I'm alive or not. It gathers all the result in a matrix and send the matrix to the user interface. That's all, okay? So yeah, I think you have understood how this thing works, but just to give you an idea. So this is an instance of my game of life. So you have a big board. You have like 5,000 cells in this case. And as I said, every cell here is a virtual thread. Plus, I have one more virtual thread for the coordinator. Okay? So this is from where I started. This is Elliot's project. But then I wanted to put this thing at work. I wanted to benchmark this thing. And the most important, I wanted to compare the behavior of this thing with both native and virtual threads. So I forked the Elliot project, and I create lots of degree of customization, and I put all this degree of freedom inside a JMH benchmark. So in this, you know JMH, right? JMH is this tool to create benchmarks in Java, where you, in a right way, meaning that it takes care for you of having a reasonable warming up, because taking measurement and stuff like this. And you can create a benchmark with different parameters. So all these parameters are orthogonal to each other, and you have different instances of this harness running with all the combination of these possible parameters. So I'm trying this thing with 3 different dimension of the board, with less than 1,000 cells, around 5,000, and almost 50,000 cells. Okay, and then I changed the original project to make it possible to run with both virtual and native thread. And then I added a policy to not only have a thread per cell implementation, but also a thread per core implementation, because I wanted to check the differences. And I added a few different implementation of the communication channel that we saw before. Okay, so the very first thing that I tried is, again, introducing the possibility of running this thing with both virtual and native thread. As you can see, the code is very similar to the one that you saw in the former example. I have this Boolean switch that allows me to take a native thread from a pool, or simply a a virtual thread. By the way, this is something that I didn't say, but since virtual thread are a very, very light data structure, a very, very light object, you don't need to pull them at all, okay? We are used to have pool of threads for native threads, again, because they are a costly resource to be created and also a scarce resource, but you don't need to use any sort of pool for virtual thread. And then what I do is having this method that calculate a single frame, but now I'm not sending anymore the frame, the matrix of liveness to the user interface, but this frame is consumed by JMH. So what I'm measuring in my benchmark is in practice how many frames per second I can do with a specific implementation. Okay, so this is my score. The more frame I can do, the faster my that particular instance is going. Okay. So let's start seeing some result. Of course, the very first thing that I want to compare is exactly the same thing with different dimension of the board using both virtual and native thread. As you can see here, for both the instance with 1,000 cell and 5,000 cell, the virtual thread implementation is around 7 times faster than the native thread one, which is expected, but it means that this thing is really working as expected. And of course, I couldn't run the native thread distance with the biggest board because simply my machine cannot create 50,000 native threads. It just goes in out of memory. Okay, so after with this result, I wanted to better figure out, okay, why I'm getting this result. Okay, let's dig into this a little more. So I created a few flame graph. How many of you can read a flame graph, by the way? A few, okay. Just to let you know, a flame graph is a very visual way to profile your Java application. They create this very nice visual representation. The things that you see here are sampling of the stack in a given moment. So you are sampling a stack and you are aggregating this stack in this colored tower. The color has a meaning. So what doesn't have a meaning is what you have on the horizontal axis. On the horizontal axis, you don't have time. They are just the method ordered in a random way, typically in alphabetic order, but it's not important. Okay. What is important is the vertical axis where you see the stacks, and the frame of these stacks have different columns to mark different kind of invocation. With the green, you see plain Java method. With this light blue aqua color, you see inline the Java invocation. In orange, you see invocation job performed in the kernel space. So typically, you see thread context switch because native thread context switch because, as I said, it happens in the kernel space. With red, you don't see much of it unless you don't have some JNI invocation. And the yellow, you see C++ code. Typically, you see the job made by the garbage collector. Okay, so I try to create flame graphs for these two different run that I made with 5,000 native thread or virtual threads. And this is the result for native thread. In purple there, I put in evidence the method called by the JMH benchmark. So there is the method that is reading the matrix for a given frame in a given run, okay? And all these things are the 5,000 native thread that I have in my run. Of course, you cannot read much of them, but if I zoom of any of them, you can see that there are a lot of these orange thing that are the context switch made in the kernel space, as I said, okay? Now, let's see Let's give a look to the virtual thread implementation. This is quite interesting, I believe, because it gives you really an idea of how virtual thread work. I have 8-hour here. Why 8? Because I'm seeing the native thread there. I'm seeing the carrier thread. As I said, my machine has 8 cores, so I'm seeing the 8 carrier thread. And now that purple thing that is the proper benchmark thread, which run in its own thread, in this case in a virtual thread, you don't see it anymore in one single thread, but because of the work stealing algorithm of the fork join pool, you see distributed it a bit in all carrier, okay? So this is the effect of the fork join pool, which is interesting to see. And the other interesting thing to see here is that I don't see that orange colors anymore. So no switch, no context switch in kernel space anymore, okay? And this is the big gain. In fact, you can run JMH with this context switch event to count the context switch. And if you do this, the difference are dramatic. In 1 second, you see that with virtual thread, I had around 10 context switch, and with native thread, I had around 50,000 context switch. So this is the huge difference, right? Because they are made in the kernel space. So if you profile this thing with htop, you will see that more or less, more than half of the time of the native thread execution is wasted in the kernel space doing context switch. Okay, that's the big gain. Okay. Mystery solved. This was the first attempt that I made. The other thing that I wanted to check if I could do better by changing the implementation of the communication channel between two threads. Okay, so this, as I said, this communication channel is a monodirectional blocking channel. I create an abstraction of it. As I said, in the CSP paradigm, this channel is actually a rendezvous between two threads to make a thread to say to the other, okay, I'm done, you can go on. So I created this abstraction blocking rendezvous. Of course, the blocking channel, the original blocking channel is one of the implementation, and I created 3 additional implementation to check if I could do better of the original blocking channel. So I used a linked transfer queue instead of a blocking channel. This is a blocking queue. This is also data structure that is available on the JVM. It has a variation of the Michael Scott lock-free algorithm, so it should be a little bit faster of the original blocking queue. And then I have 2 custom-made implementation. The first custom-made implementation is because I noticed something. I noticed that in this particular instance, I don't need really a queue. I'm just making a thread to write a value and making another thread to read that value. So I don't need really a queue. I just need a synchronized access to one single value. Okay? So I created a locked implementation to read and write that value. I don't want a complete queue. I just need to read one value. So I leverage the one of my knowledge of the domain to try to create something better. Okay? And then my dear friend Francesco Nidgro came over and noticing something even more important that I didn't. By the way, okay, I try to have fun of Twitter, but if you are really serious about performance in Java, you probably should follow this guy. Then my dear friend Francesco noticed said something even more important. Not only I need in this instance to read and write one single value, but in one given channel, the writing thread is always the same, the reading thread is always the same. And by leveraging this further bit of information, this further small domain knowledge, it could create an even better an even better implementation of this by fine-tuning, synchronizing only the two threads that are involved in that conversation on that specific channel. Okay, so I tried these 4 different implementation of the channel. First with native thread, I didn't see much differences here, but it was sort of unexpected, you know, because we already know that the bottleneck in that situation is somewhere else. It's in that huge context switch work made in kernel space. Okay, so I didn't see much difference, but instead, if I run this thing with virtual thread, then I see a difference. With the original blocking queue, I can do 118 frame per second, and then with the locking free algorithm, it was a little better. It was even a little better with my implementation using a single value instead of a whole queue. But with Francesco's algorithm, it was a real game changer. It goes more than 2.5 times faster of the original implementation. So what is the bottom line of this is, yes, virtual threads are great, but it's even greater if you use your knowledge of the domain to improve the performance of your code. Okay, so I wanted to figure out what's going on here. Now in purple, you see the call of the on the reading of the blocking rendezvous. This is the blocking queue, and you see a lot of them. In this instance, you see 1,900 sample, and in this other instance, which is with Francesco data structure, you just see 600 samples, meaning that this thing is really 3 times faster than the other, and exactly is what the thing I measured with my benchmark. Okay, and then I wanted to do quickly another check. Okay, so far I played on the virtual thread fields, meaning that I'm having tons of threads and making blocking call of them. Of course, this is not fair if you want for native threads. So I wanted to create another degree of freedom in this application and say, okay, in this instance, I want a thread per cell implementation, which is the thing that we have seen so far. So the number of thread is equal to the number of the cell plus 1 for the coordinator. And then I created a second implementation where the number of thread is equal to the number of core available on my machine. So I just have 8 thread, virtual or native, and I split the cell in group to stay on 8 minus 1 thread, because the 8 thread again is used for the coordinator. Okay, so a cell group is just a list of cells where each group first notify the liveness of the other and then gathers the state from the neighbors and communicate its own state to the coordinator. Okay, and if I do this, of course, I'm playing more on the native thread fields, and in this case, if you see with this thread per core implementation, the performance are much better. Well, are better, not that much better, but are better for native threads. So what I wanted to say here is that if you change the rule of the game, of course, very likely you are also changing the winner. You are choosing the winner in a different way, right? So just a few conclusions about this. Virtual threads are not faster thread. Yes, they look faster in CPU-bound task, but just because they are not fair, and probably you don't want to get there. But they are very great in specific situation, which is the most common situation. It's very common that you do a blocking operation that you need to wait, and they are really, really good to wait unless they are not pinned. So pay attention to pinned thread. They are there to maximize the usage of your resources, but without the madness of reactive programming. Okay, so it's reactive, it's sane reactive programming. It's more readable reactive programming. That's what they are. So are they good? Yes, they are really, really good for IO bound operation. If you don't mind about fairness, probably they are also good for CPU bound operation. But the bottom line is that they are not drop-in replacement again for native thread. So they are a different tool in your toolkit. You have to know them, and you have to choose. It's up to you as a developer to choose the right tool for the job at end. Okay, so this is the bottom line. But the real bottom line is that still domain knowledge matters a lot if you care about performances, if you know the constraint of your domain and you are able to leverage them, you can create a super performant code. Well, the technology use matters a lot, but also the optimization that you can provide by leveraging the domain knowledge also still matter a lot. So keep your brain on, okay? And that's all for me. Thanks. I don't know if I have just 1 minute for question, or I can take it offline if you prefer. Yeah, let's grab some coffee, and please feel free to ping me offline.